Good morning, students. In last lecture we have discussed about lossless transmission line. In that case we finded out the different parameters of the line, that is alpha, beta, gamma, characteristics impedance, Z0, phase velocity. Today we will try to find these parameters in case of distortionless transmission line. So the necessary condition for distortionless transmission line is that the ratio of the resistance and inductance, this is from R plus j omega L, the ratio of R and L is equal to the conductance divided by capacitance. So this is the necessary condition for lossless transmission line. Now let us try to find the different parameters, that is alpha, beta, gamma, characteristics impedance and phase velocity in the case of this type of transmission line. So let us start from gamma. We know that is nothing but alpha plus j beta. We know in case of the line alpha plus j beta can be written as R plus j omega L times G plus j omega C, Z multiplied with admittance Y. So if we will take R from here, then we can write R as common from this term and G common from this term. Then we can write 1 plus j omega L by R here and 1 plus j omega C by conductance G. We can write like this if we have taken R and G common from here and here respectively. And as the condition for this type of transmission line is R by L should be equal to G by C. So G by C can be, C by G can be equal to R by L. We can write it down. So here we can further simplify RG 1 plus j omega L by R 1 plus j omega L by R. C by G can be written as L by R. We can write it down like this, and further it can be, this term will be out of the square root, so it will be 1 plus j omega L by R times square root RG. And if we will further simplify, we can find RG plus j times RG omega L by R. Okay, and from here we can say it is alpha plus j beta. So alpha is equal to square root RG and beta is equal to omega L by R square root RG. Now if we will take the L by R inside, then it will be omega under root RG. It will be L square divided by R square. We can write it down like this, and this R and this R will be cancelled out. L by R can be written as C by G. So here it will be G times L by R will be C by G, and one L will be left out. It will be further simplified form LC. This is nothing, just phase constant. So in case of distortionless transmission line, alpha is square root Rg and phase constant is omega under root LC. Now after alpha and beta, the next parameter that is required to discuss here is characteristics impedance, and we have discussed the formula for that. J omega, this is the ratio of R plus j omega L divided by admittance term G plus j omega C. In case of distortionless transmission line, let us try to simplify this. If we will take R common from here, then it will be 1 plus j omega L by R, and from the denominator side, if we will take G common, then it will be 1 plus j omega C by G, and R by G is square root R by G times L by R is equal to the C by G. So these two terms, after being equal, it can be cancelled out. The remaining term will be square root R by G. So this is the characteristics impedance, and R by G can be written as under root L by C. From here, R by G can be written as L by C. So that we know in the plane wave propagation, the intrinsic impedance is nothing, that is equal to the square root L by C. Here that is same characteristic impedance is under root L by C. Now the phase velocity, the simple formula that we have, omega by beta. Beta we know from here, so we can say omega divided by omega square root LC, that is 1 by square root LC. This is the phase velocity. So in this way we have the different parameters in case of distortionless transmission line, that is alpha, beta, impedance and velocity. Now let us solve one example to find the different parameters of the transmission line. Either we can say to find the equivalent circuit of the transmission line. So for that, the parameter that is given to us is the propagation constant, that is gamma is equal to the 2 plus 5j, and the characteristics impedance is equal to the 50 ohm, and omega is given as 10 to the power 6 radian per second. Now if we have these parameters, then we have to find the parameters of the transmission line, primary parameter, so that we can find the equivalent circuit of the transmission line. So to find the equivalent circuit that we have studied is conductance, capacitance, resistance, inductance, conductance, capacitance. So we have to find these parameters, and we know alpha is equal to square root Rg. In case of lossless transmission line, the alpha is 0. In case of, we have derived this, as it is not 0, so it means the discussion is about distortionless transmission line. Alpha is equal to square root Rg, that we have calculated here. The next equation we have phase constant is LC, and the third equation that we have the impedance is equal to L by C, that is R by G. The informations that we have from the given parameters are alpha is equal to 2, beta is equal to 5, and Z naught is equal to 50, and omega is equal to 10 to power 6. We have these informations. So if we will multiply, we wish to find R, then we can find, if we will multiply this term with this term, then G and G will be cancelled out. The multiplication of square root R and square root R will be R. This side will give us R. So we can get hint from here that if we will multiply, name it equation 1, 2, 3. So if we will multiply equation 1 with equation 3, then that will give us square root Rg multiplied with R by G. Gg will be cancelled out, square root R will be R. So alpha is known to us, that is 2, from here 2, and Z naught is 50. So R will be equal to the 100 ohm. So from here we find R is 100 ohm. Now this second parameter that is required to know is L. The remaining parameters are L, G, C. So for that purpose, if we divide this from this, then R will be cancelled out, G will be there. So just do that. 1 divided by 3. So after that we will get alpha by Z naught will be square root Rg divided by R by G. So these two terms will be cancelled out. G and G will give us out G outside from the square root. So R alpha is 2, Z naught is 50, G will be equal to the 0.04 mho per meter. Okay, these all are in per unit length. So we know R, we know G. The next remaining parameters are L and C. And to find the L, what we can do? If we will multiply this with this, then C terms will be cancelled out. Multiplication of square root L, square root where L will give us L. So what we can do? Multiply 2 with 3. If we will do that, then we will get beta Z naught will be equal to the L, and so L will, from here L will be, beta is 5, Z naught is 50, omega is 10 to power 6. So from here we can say it is 2.5 into 10 to power minus 4. Okay, either we can say 250 micro Henry. Okay, this is Henry per unit length. Now the next is remaining element is C. So for that purpose, if we will divide this with this, then L will be cancelled out, C term will be there. So divide 2 from 3, it will give us beta divided by Z naught, that will be omega C, and from here C will be, beta is 5, Z naught is 50, and omega is 10 to power 6. So multiply from 2, it will be 10 to power 8. So overall it will be 10 to power minus 7 farad, or we can say 0.1 microfarad per meter. So in this way we have C, we have L, we have G and R. In this way all parameters of the equivalent transmission line is known to us. Now let us talk about the reflection coefficient in case of transmission line. This term is already have been discussed in case of uniform plane wave, and in that case we came to know that when wave is traveling from one medium to another one, then part of it is get reflected back and part of it is transmitted to another medium. In that case we try to find the relationship between the reflected and incoming wave and transmitted and incoming wave. Similarly, in case of transmission line, we will define the reflection coefficient. Though there is no different medium, the conductor is same, so the reflection, how it does occurs, it is important to know. So for that purpose, let us assume that this is the source, this is internal impedance of the source, and the current that is flowing is I in, or we can say I naught, because this is the current considered at input of the transmission line, that is at Z is equal to 0, and the length of the transmission line is considered as L. So for L length, Z is considered as L at receiving end, and at this point the potential is considered as VL, and the current that is entering here is I naught. The current at the load side is IL. This is ZL. Now the important question is that when the medium is same, then how reflection occurs in this. So that becomes possible only when the load impedance does not match to the characteristics impedance of the line. So if it is not following this, then it is the reflection takes place in this condition. And we know that the definition of the reflection coefficient is a reflection coefficient is the ratio of the reflected wave divided by the incident wave. The VSZ can be equal to the forward traveling wave, voltage wave, this is forward, plus reverse traveling wave. Reverse means in negative direction of the Z. And similarly, if Z is, this is at Z is equal to any particular value. Now if Z is considered at this point at L, then we can say Vs at Z is equal to L can be considered as the forward traveling wave, voltage wave, plus reverse traveling voltage wave. This is nothing at VL, at Z is equal to L, the voltage is VL, we can write it down. Similarly, okay, note it down, equation number 1. Similarly, in case of current, we can write at any point by Z naught e to the power minus L. At here, the reverse can be written as e to the power L divided by Z naught. Let me explain how it is minus here. We know V naught divided by I naught. Forward traveling wave, it was characteristic impedance, or reverse voltage wave, reverse current wave. Here it becomes minus, then it will be equal to the characteristic impedance. So this term is placed here, it will come here. I naught negative will be equal to minus V naught negative divided by Z naught, and remaining terms will remain same. So in case of V naught and Z, that is placed at the place of I naught, so it should be with minus sign. So that comes from here. And if we will further simplify, that is here it is at Z, sorry, at Z is equal to L, at this length we can say IS will be IL, or we can say IL, the current that is flowing here is IL. It will be equal to the V positive divided by Z naught e to the power minus gamma L minus negative Z naught e to the power gamma L. Now consider it equation number 2. In this way we have two equations for further simplification and analysis, so that we can find the reflection coefficient just by placing the value from here in this formula. Now reflection coefficient can be defined as coefficient can be equal to the, for voltage wave it is gamma V, or that is at the load end, so we can write it gamma load as well. It is equal to the reflected voltage wave, as we are talking about voltage. So reflected voltage wave e to the power gamma L. L is the length of line at the receiving end divided by transmitted incident wave that we have here. So negative divided by V naught positive e to the power 2 gamma L. Anyway, if we are able to find these two terms, then we can put it here and simplify this to find the gamma V, or we can say gamma load. So for that purpose, let us take help of these two equations. That is, if we will multiply IL from Z naught and we will add these two, then these two terms will be cancelled out. We can have the single equation in terms of V naught. It seems to be like that. So what we can do, we can add equation number 1 with equation number 2. So if we will do that, then we will get VL plus Z naught IL, just I am adding, will be equal to the, this term will be cancelled out, the remaining term will be V naught e to the power minus gamma L plus V naught e to the power minus gamma L. So ultimately it becomes 2 V naught e to the power minus gamma L. And from here, if we will bring this term, if we want to find V naught, positive, to put it here, then what we can write, V naught positive can be written as VL plus Z naught IL divided by 2 e to the power gamma L. We can write like this. And similarly, we can find V naught negative. That can be possible by subtracting second from first. So similar to this term will be cancelled out and this negative term will be left out. So we can see VL, what we can write? Equation number 1 minus equation number 2 minus. So if we will do this, then we will have IL Z naught from here, and this term will be minus, this term will be minus, minus cancelled out, it will be plus. V naught minus e to the power gamma L, so it will be 2 times this plus this. And if we will try to keep V naught outside, then it will be IL Z naught divided by 2 e to the power gamma L. Now put these two values from here to this equation, or we can say in this equation, to find the gamma V. So gamma V can be written as V naught negative, that is this one, VL minus IL Z naught divided by 2 e to the power gamma L with minus sign, divided by V naught positive, that is V naught positive, that is VL plus Z naught IL divided by 2 e to the power gamma L. Okay, and gamma V is the ratio of this multiplied with e to the power 2 gamma L, that is already there. So what we can write? Gamma V. Hope it is okay. So this term, once it will be at numerator side, it will be minus 2 times, and this 2 times, and this minus 2 and this plus 2 will give you e to the power 0, that will be 1, and it will be 1, this 2 and this 2 will be cancelled out. The remaining term will be VL minus IL Z naught, VL plus Z naught IL, that is gamma V. From here, what we can do? VL is equal to IL ZL. So here we can write IL ZL minus Z naught, taking IL common from here to and here. Similarly, IL can be common from here to here. It will be ZL plus Z naught. These two terms will be cancelled out. Now the reflection coefficient, that is for voltage, that will be gamma V, or we can say gamma load will be equal to the ZL minus Z naught divided by ZL plus Z naught. L means it is receiving end. So relate this from the plane wave propagation, that is the reflection coefficient was, in that case it was E, that was impedance 2 minus impedance 1 divided by impedance 2 plus impedance 1. If you can recall, then you will find this was the gamma E, and this is medium 2, medium 1, medium 2 plus medium 1. Similarly, ZL load side Z0 ZL plus Z0. In the same way, we can talk about the case of current, and in the case of current it is minus V0 divided by V0 e to the power gamma L from here, e to the power minus gamma L from here, so it will be 2 gamma L in case of the reflection coefficient for current wave. So just concentrate this. This is equal to the voltage one, that is this, except negative sign. So what we can find from here, it can be equal to the gamma. In case of I, it will be equal to the minus gamma in case of voltage, that is minus ZL minus Z0 divided by ZL plus Z0, and after further simplification it will give us Z0 minus ZL divided by Z0 plus ZL. This is the reflection coefficient for current wave. And one thing should be very clear, that these are at the load end. Okay. Now we will try to find out at any particular length other than the length of the line. So we will try to find the reflection coefficient at any other length that is in between the transmission line. That we will do in next term. Thank you.